So in this question, we have a space capsule, and then we have astronaut that acquires speed by kicking on this space capsule. So we're asked 3 questions. First, what is the change of the speed of the space capsule? Let's first give everything a letter. Let's call the astronaut A and call this B. So this is an isolated system, so we can use the conservation of momentum. P initial equals P final. P initial, nothing is moving initially, so it's 0. Afterwards, astronaut has a velocity v prime, and the space capsule has its own velocity v prime. We'll ask what is the change in the speed of space. So what is vb prime? V prime equals, from this equation, negative mava prime over mb. So, and then we plug in the numbers. It's negative 125 kilogram times 2.5 meters per second over mb is 1900 kilogram. So this gives us negative 0.1645 meters per second. We don't need that much significant digits. We need to round it to negative 0.16 meters per second. So the space capsule will also move and with a velocity of 0.16 meters per second, and the negative sign indicates that it will be moving in the opposite direction as the astronaut. So part B, if the push lasts 0.6 seconds, what is the average force exerted by each on the other? So firstly, because of the Newton's third law, we know the average force exerted by the astronaut to space capsule, and the opposite will be equal and opposite. It will be the same magnitude and in opposite direction. So because of that, we really just we only need to calculate one. We don't need to calculate both. Like, as a double check, you can calculate both, but they'll be the same. So here, let me just use the astronaut to calculate the force. So I have F average equals delta P over delta T. This is just Newton's second law. It's a more general form of Newton's second law. And the change of momentum is m delta v over delta t. So it's 125 kilogram times the change of it is just 2.5 meters per second because it was initially at rest. Over delta t is 0.600 second. This gives me a force of 521 Newton. So the average force of the astronaut is, of course, it's in the direction that the astronaut is traveling, and the average force exerted by the astronaut on the space capsule will be the same magnitude, but in the direction opposite to the travel of the astronaut. Now, part C. What is the kinetic energy of each after the push? So we just use the formula of the kinetic energy because we already know the velocity of each after the push. So for the astronaut, it's half of mava prime square is 1/2 of 125 kilogram times va prime is 2.5 meters per second square. This gives me 391 joule. And the kinetic energy of the capsule is 1/2 of mvvb prime square. That is 1/2 times 1900 kilogram times we can use the result for period. It's 0.16 meters per second, also squared. So that gives us 26 joule. So we can also say that in this process, the momentum is conserved, but the kinetic energy is not conserved because the kinetic energy was 0 before the push, but it's non-zero after the push.